doesn't. All it does is like do. We'll see. But I'm happy. I'm very happy. All we need to do is get and the test levels like. Although we can work on that now, that's good. That's very good. Is there tests in this class next week? And when's our paper?
Today's topic, I used briefly last time, probably will not be Wednesday. So the issue is getting electrons from NADH to oxygen. So the issue is electron transport chain, and then protons get pumped.
I don't think it's
with that. So this is the complicated version of the figure from the book. It shows what's going on. So this is the membrane, the inner membrane of the mitochondria. This is the matrix side of the mitochondria, the space. Note that they call these P and N sides. So P refers to positive charge. That's because protons are moving to this side of the membrane, which gives it a net positive charge. So the N side is where there's a net negative charge. All right, so this is a complicated picture. I'm going to use a slightly simpler. This is from the same book. So I'm not sure why I have two versions. This is the cartoon version. So the overall reaction, remember, right, like this. That the issue is to get electrons from NADH to oxygen. To make water. And so what both of these figures show is that this is accomplished by a long chain. So there's the NADH, and there's the oxygen way over there. And so the electrons that are in the NADH have to go through this long sequence of events. So this is the electron transport chain. And the electron transport chain made up of 4 enzymes plus many electron carriers. And a few of the electron carriers are shown in this figure, and I'm going to go through them and a little bit their structure and a little bit their chemistry. The 4 enzymes are these big blocks here. So a few of the electron carriers are shown, but actually within each of these large enzymes, there are a fairly large number of electron carriers that are not shown explicitly in this figure. I'll show the details of a little bit of them later on. But the electron carriers, I sort of all right, these are the enzymes. So the 4 enzymes are listed in this table, and they each have a name, like all enzymes do. And you can learn the names, but I'm going to refer to them as complexes 1, 2, 3, and 4. All right, so it's sort of like the previous thing, where this suffices. And I won't ask you to know these names. Of course, as always, the names sort of remind you what the enzyme does, so it might be useful in that respect. But I'm going to refer to them as complexes 1, 2, 3, 4. So each of these is a membrane-bound enzyme. It's embedded in the inner membrane of the mitochondria. As you see, these have very large molecular weights, and each of them is composed of multiple protein subunits. Complex 1, you see the first one's complex 1, a huge number of subunits. This protein cytochrome C is not one of these enzymes. I'll come back to it in a minute. Right? And each of these enzymes has several electron carriers that are bound to the enzyme, as I indicated in a minute. All right, so I'll say a little bit about each of these carriers later on, or each of these enzymes and what they do. But I want to focus first on the electron carriers. So I like to group the electron carriers into sort of 2 broad types. The first broad type I'm going to call diffusible. second broad type are the ones that are enzyme bound. And that remain bound permanently to whatever enzyme they're bound to. These are also known as prosthetic groups. Essentially, they're coenzymes. So, again, all these substances are to get electrons from NADH to oxygen. So, I can go back to this figure. Let me start with a diffusible one. So the first diffusible one is an enzyme, is a molecule called coenzyme Q, which is abbreviated as CoQ or just as Q. It's also known as ubiquinone. I guess because it's ubiquitous.
Is this the same thing as
Pardon me?
Is this the same thing as coenzyme Q10?
Yeah, it's coenzyme Q10. You can buy it in health food stores. So the structure of coenzyme Q, the most important part is this. So that's a quinone. So this is the oxidized structure. Oxidized. There's other stuff attached here. I think there's methoxy groups here, which aren't that important, but there's another important part of this molecule. So there's a methyl group here. The other important part is what's attached here, which is this. And so that's a repeating structure. There are n of these, or n I guess is 10, so we know it's 10. So it's a long chain of these. So these are 5 carbon units are called isoprene units, and they're just a long chain of these. So this molecule then there's 2 important features. One is this 6-membered ring, the quinone ring. So that's where this molecule can accept electrons. The other important part is that there's this very long hydrophobic chain. And so this molecule is completely insoluble in water. All right, so this is, you could say it's dissolved in the membrane. It's like it's a lipid, so it can be embedded in the membrane. It can diffuse around in the membrane, but it can't leave the membrane to go into an aqueous environment. So it's diffusible in the sense that it diffuses around the membrane. All right, so this is the oxidized form, the quinone form. So this would be the form you would call ubiquinone. And so this molecule can be reduced, it can accept electrons. And yes, there are 10 of these 5 carbon units.
Oh, so it's just
Yeah. So this molecule can accept 2 electrons and 2 protons, and it can be reduced to what's known as the hydroquinone form. The hydroquinone form looks like this. It's also the 6-membered ring. It can accept 2 electrons and 2 protons and become reduced to the hydroquinone form, which the peripheral groups are unchanged, but the 6-membered ring takes on this structure. So this is a reduced form. You could call this coenzyme QH2, or co-QH2, or QH2, I think the book they just used QH2. You can also call it ubiquinol. You'll see this name in the book as well. So the only thing that changed was the 6-membered ring and the oxygens. The rest was unchanged. So this is how the oxidized form can accept electrons and become reduced. And so this is an intermediate in the electron transport chain. I guess you see it there. So there's the reduced form, there's the oxidized form Q. Right? Now the important thing about this molecule, coenzyme Q, is that in addition to accepting 2 electrons, it can also accept 1 electron at a time. So if it accepts a proton and 1 electron, you get a partially reduced form, which has this structure. Again, all the peripheral groups are unchanged. And, yeah. So this is known as a semiquinone form. This is a radical. The dot represents the 1 electron that is sitting on that oxygen. But if that electron is delocalized over the whole structure, you can write a bunch of resonance structures. I think you could rewrite this as co-Q H dot or QH dot. And that's the semiquinone. So the oxidized form can accept 1 electron and make this stable semiquinone form. The semiquinone form can then accept the 2nd electron and become the fully reduced quinone form. And this turns out to be an important property of this molecule because in the course of these reactions, this is going to have to do that. It's going to have to accept 1 electron at a time. So that here's now the figure from the book that shows all these structures. Fully oxidized form, the semiquinone with the 1 electron, unpaired electron, and then the fully reduced hydroquinone. All right, so this is diffusible. It diffuses in the membrane. It was shown on the previous slide. We'll come back to it, how it actually fits in. There's a second diffusible electron carrier. Which is also involved.
Bless you.
So wait, in the fully reduced form, you wrote
But the second diffusible electron carrier is a protein called cytochrome C. So cytochrome C is a small protein. In this figure, here it is up here. So it's on the P side of the membrane, and what they're showing, this dashed line indicates this protein that can diffuse around in the aqueous environment of the intramembrane space. So this is a small protein. It's about 100 and some amino acid residues size. There it is. This is the protein for humans. And the important thing about this protein is that it has a heme, which is bound to the protein. And in the center of the heme is an iron. So that little orange sphere is the iron atom in the center of the heme. And then this green thing is the porphyrin ring of the heme. And you can make out the 4 blue oxygens that are bound to the iron. And then the rest of it. So this is a heme. It's very similar to the one in hemoglobin, not identical. And so let me remind you what the structure of this is. So remember that heme contains an iron. And the iron, in this case, the iron can either be in the +3 or the +2 oxidation state. Let's start with it in the +3 state. Remember that the heme iron is bound to the 4 nitrogens, and each nitrogen is part of a 5-membered ring. And each 5-membered ring is bridged by 1 carbon. So that's sort of what the orbital ring looks like. Right? So the blue spheres in the center here are the four nitrogens, the irons in the middle. So that's only part of the structure of the heme. So here's the actual structure from the book. Right? So first of all, there's lots of double bonds in here. These are all conjugated. Delocalized electrons over the ring. And then there's peripheral groups that we tend to forget about. But I just point out that here, these peripheral groups, in hemoglobin, these are just carbon-carbon double bonds. But in this, in cytochrome C, these are actually bound covalent to two cysteine residues part of the protein. So it turns out that this heme is actually covalently bonded to the cytochrome C protein. Okay. So this is a partial structure of the heme with the iron, but this would be the oxidized form because the iron is in the iron plus 3 state, and this can accept one electron and be reduced to the iron plus 2 state, and that iron is still found in the center of the porphyrin. So this is a highly schematized version of the reduced form of this heme, which is covalently bonded to cytochrome C. So note that the heme can accept only one electron. So unlike coenzyme Q that could accept one and then a second one, or NADH, which always carries 2 or 0, this guy only can carry one electron at a time. And that'll be developed later on as well. All right, so those are really the two carriers in this process that can diffuse from one enzyme to the other. All the other carriers are covalently bonded, or tightly bonded, not necessarily covalent, to the enzymes that diffuse. Good question. So no. For this course, I don't know, what did I say last semester? Probably had to know the iron and the nitrogen. You don't have to know the detailed structure. I think in the past I've sometimes shown pictures of that, like on exams, and so you'll be able to recognize it. All right, so let me discuss the molecules that act as prosthetic groups. So again, these are the things that are tightly bound and remain tightly bound to whatever enzyme uses them. There are, I guess, 4, of which I'll comment on 3. The first type are flavins, and by that I mean either FAD or FMN. And there are a number of these bound to one or another of the enzymes. So flavins, remember, let's see, there's a nitrogen, and then, so remember these two nitrogens are important, and then let's see, here's a carbonyl, another nitrogen, carbonyl, H's, and okay, this would be, and then there's a second ring over there. Some other stuff attached to this ring.
That one is just an aromatic.
Yeah. So we saw this before, and I think I said what you should be able to draw, and you don't need to worry about drawing anything more than this. Remember that this is attached, though, in FMN, this is attached to ribose, which is attached to phosphorus. So that's flavin mononucleotide, or FMN. So this would be the oxidized form. And it's these two nitrogens that are the key. And I guess I didn't draw my double bonds correctly. Oh, that's way too many bonds. So there it is. So remember that you can add 2 electrons and 2 protons, going back to pyruvate dehydrogenase. And so reduced form, the Fa4. So that would look like that, and the rest of it isn't changed. So this would be, if this is FMN, this we call this FMNH2, and that's the fully reduced form. But I mentioned this last time, I think, when this molecule first appeared. FMN can also accept one electron at a time as well. So FMN, like coenzyme Q, can be reduced by 2 electrons and 2 protons, but it can also accept 1 electron and 1 proton. And in that case, you get a structure that looks like this. Draw this. So here's the proton, there's the 1 electron, and I think that's an acceptable structure. Fortunately, it's on the next slide. You can actually write a number of resonance structures of this. Okay, so this is a structure in the float. So that's a better structure. So they're showing this is one resonance structure. You see it got a negative charge up here in this oxygen. So there's a number of resonance structures, and so as long as you can write a reasonable resonance structure, you're okay. So I think I'm going to leave it at this. So this is again a semiquinone form. Right, so again, this is stable. Free radical has 1 unpaired electron, right? And so you have this partially reduced form. So again, as for coenzyme Q, you can have the fully oxidized form accept 1 electron to make it partially reduced semiquinone, and then this can accept a 2nd electron and a 2nd proton. So again, it can accept ultimately 2 electrons, but it can accept them 1 at a time, and it can give them up 1 at a time. There is a significance, so we'll come back. So the fact that these guys can accept 1 electron in a way that's stable is important. The other thing just to point out is that this is the complete structure of FAD, which has the flavin ring, ribose, phosphoryl groups, another ribose, and adenine. So it's flavin, adenine, dinucleotide, FAD. And then remember that FMN stops here. So FMN is a mononucleotide, the flavin plus the ribose plus the 1. And the rest of this, well, it's not important, but it's important to know that there is a difference between these. So this, as before, for other enzymes, it's come up, this stays tightly bound to whatever enzyme you need. So that's one type of aesthetic group that stays bound always to enzymes. The second type are what are known as iron-sulfur clusters. And so iron-sulfur clusters come in several forms. And one of the important forms has this structure, has an iron, which is covalently bonded to a sulfur atom. Covalently bonded to a 2nd iron and a 2nd sulfur atom. So this is known as a 2-iron, 2-sulfur cluster. This is then covalently bonded to an enzyme because the irons are then bonded to the side chains of cysteine residues that are part of the protein. So this would be the full structure of a, we call an Fe2S2 cluster, or 2-iron 2-sulfur cluster. So those are, certain enzymes have that form of cluster. There's another form that's even more elaborate. So this one has a similar structure. It starts out similar. So 2 irons, 2 sulfurs, but then there's 2 more irons. And these 2 bottom irons are also bonded to sulfurs. And I think that's what it looks like. And then each iron is bonded to a cysteine. So you have this nice cubic structure of the irons and the sulfurs, and it's hard to draw it. So fortunately, this figure from the book shows this. So here's the 2-iron sulfur cluster. Here's the 4-iron 4-sulfur cluster. This is a nice drawing. You can see that the iron and sulfur atoms make the vertices or corners of a cube. And then each iron also is bonded covalently to the protein via these 4 cysteines. Right, and then this one over here, hardly the first name of an iron sulfur cluster, but it's a single iron atom, and so you can have that as well. Now, here there's 1 iron, so it's going to be iron plus 2 or plus 3. But here there's 2 irons and 4 irons, and so you might think that these can accept lots and lots of electrons. But in fact, they can't. They can accept only 1 electron. So this cluster might, for example, have 2 irons, possibly in the plus 3 oxidation state. So that would be the oxidized form of the cluster. And if that is the oxidized form, then this can accept 1 electron, and you could write it like this. Where I've indicated that it was this iron that got the electron, right? But in fact, these are delocalized systems, so the electron is actually delocalized over that cluster. It's not situated on one or the other irons. Right? And so each of these, even the one with 4 irons, will only accept 1 electron. Another way to put it is that the reduction potential for trying to put another electron in there is very, very low and negative. So for any, there's no biologically interesting forms that are carrying more than 1 electron. Right? So these are electron carriers that they can be alternately oxidized or reduced, but always and only by 1 electron. So that's the second important kind of prosthetic group. So the third important prosthetic group is hemes. So in addition to the heme that's bound to cytochrome C, various of these enzymes also have 1 or more hemes bound to them. And I'll point those out as we go along. Their structures are similar to one of cytochrome C, although not necessarily identical. That's all I'm going to say about those. But remember, these can carry only 1 electron. And the very last one that I just mentioned, because it's indicated on one of the slides, is copper. And these are copper ions that are bound, as individual copper ions to the protein, and these can be in the +1 and the +2 state. And so again, these can carry 1 electron. So that's the list. I think that accounts for everything. That is to enable electrons to get from A to oxygen. Yeah. So here's again this table that shows the 4 complexes. Now again, they list cytochrome C, but there's a footnote that it's not part of any of these enzymes. And here are the prosthetic groups. So you see that There's iron sulfur clusters on several of them. Flavin mononucleotide, flavin dinucleotide, and then hemes on several. And I mentioned the copper. Complex 4 has some copper. Okay. So how does this work? I'll give an overview of, again, going back to the reaction of NADH. I'll write it this way. We'll think about, at least initially, what happens to a single NADH. NADH, a mole of NADH can react with half a mole of oxygen, and the NADH becomes oxidized back to NAD+, and you get water. All right, so now I just want to go through the broad steps by which this happens. So the electrons are first transferred from NADH to oxidized coenzyme Q to produce NAD plus the reduced form of coenzyme Q. And for this, you're going to need 2 protons. So this is catalyzed by complex 1. So reduced coenzyme Q is a product of complex 1. It diffuses out of the active site, diffuses away in the membrane, and it diffuses to the next carrier, which is actually complex 3. So reduced coenzyme Q is a substrate for complex 3. The other substrate for complex 3 is cytochrome C. So complex 3 catalyzes the reaction of 1 reduced coenzyme Q plus 2 oxidized cytochrome Cs, and that produces 2 reduced cytochrome Cs plus the coenzyme Q is reoxidized, so the electrons are passed from the coenzyme Q to the cytochrome C. And finally, complex 4 is the enzyme that reoxidizes the cytochrome C. So complex 4 is the one that actually uses the oxygen, and again, to be consistent, you need 2 cytochrome Cs, or 2 moles of cytochrome C for half a mole of oxygen, or 4 cytochrome Cs for 1 oxygen molecule. And the cytochrome C gives up its electrons and becomes oxidized, and I guess also need 2 protons of this stuff as well. Right? So that's the sequence of events. For NADH, it's complex 1, then complex 3, then complex 4. The electrons are passed from the NADH, first coenzyme Q, then to cytochrome C, and then finally to oxygen. All right, so there it is. There's a complete picture. It says what I just said. I want to say a little more detail about what happens in complex 1. So this thing represents complex 1. It has 2 parts. It has many subunits, as shown in the table in the previous slide. But several of those subunits sit in the membrane, and then it has a large part, which is also several proteins, that project out into the matrix of the mitochondria. And indicated on this slide is that NADH is a substrate, NAD is a product, oxidized coenzyme Q is a substrate, reduced form is a product. And this blue arrow represents the path of electrons from the NADH to the coenzyme Q. Note that there's also protons, so you need 2 protons to make the reduced coenzyme Q. That's those. In addition to that, there's 4 other protons that actually get pumped. Right, the pumping, the mechanism that we'll discuss on Wednesday, is coupled to this electron transfer process. but it's occurring in a sense independently. It's a separate mechanism. So we'll leave the proton pumping for later. So I want to show what goes on in its unitized way. All right, here it is in a less schematized way. And this gives us the gist of how it's, yes?
Did you just not mention complex 2?
Yeah, we'll come back to complex. This shows a less schematized way. First of all, it indicates some of the low resolution structure of the protein in the membrane, and then this part here. The electrons occur again by these, the blue arrows represent the path of electrons. What you see is that the path involves electrons, this is incorrect. The electrons go from NADH to a flavin, and then there's a series of iron sulfur clusters. And so the electrons are passed from one carrier to the next until they finally reach the active site where coenzyme Q is bound. So let me show this in a schematized way. We looked at what the structures of these things are. Let's try to get across what's going on. All right, so I'm going to indicate, let's say this is complex 1, this big oval, and complex 1 has the FMN, which is going to start off in the oxidized state. Right? So this is going to react with NADH. So NADH is going to have to bind into an active site, but I'm going to just indicate the flow of electrons, or the sort of transfer of electrons. This is a common way that redox reactions are illustrated. So the electrons are going to be passed from the NADH to the oxidized flavin to make the reduced flavin. Right? So the 2 electrons go from here to there. You could say that proton went from there to there, and we're going to need 1 additional proton. Right? And so let's say this is the matrix. All right, so that's what's shown at the bottom of this figure. That 2 electrons go to the flavin. All right, so the next thing on the chain is an iron sulfur cluster. Right? So iron sulfur clusters, remember, can only accept 1 electron at a time. So if we continue this chain, let's call this iron sulfur cluster number 1, meaning it's the one that's right there, right next to the flavin. And it's starting off in the oxidized form. So this is iron sulfur cluster number 1, and it's going to accept 1 electron from the reduced flavin. So it is now a reduced iron sulfur cluster. The flavin is going to be left in the semiquinone state, at least temporarily. It loses 1 proton. That proton goes back out into the matrix. All right, so the 1 electron was passed to that iron sulfur cluster. And then you see there's a series of iron sulfur clusters. So the electron is going to be passed from this one to iron sulfur cluster number 2. So let's put that one in. So this is iron sulfur cluster number 2, which can accept 1 electron and become reduced. And cluster number 1 is reoxidized. And I didn't leave enough room in my figure, but this could then be passed to cluster number 3, which will be reduced, etc. Right? So that's going to be the sequence of events, 1 electron being passed through this sequence of carriers. Eventually, I think there are 6 clusters in this chain. There's 3 others that are sort of peripheral. It's not clear what they're there for. But eventually, so I left out some steps. Eventually, this electron finds its way to coenzyme Q. So you have an oxidized coenzyme Q, which is going to accept an electron that was passed along by the chain, and it's also going to accept a proton, And this proton comes from the matrix side of the membrane. Okay, so we've gotten one electron to the coens on Q. All right, we still have this one electron back here. That's going to then be passed along at some point. And so you can complete the chain by having this second electron be passed along. And it's going to go to the same iron sulfur cluster number 1. Which is going to be reduced again by one electron. So a second time. And this H is again released to the matrix side of the mitochondria. Matrix side of the membrane, it turns out. So we've got the second electron is in cluster number 1. It's going to be passed to cluster number 2. To cluster number 3. And eventually make its way to the coenzyme QH2. And let's finish this by, so I left out some transfer steps. Now the second one is going to be the semiquinone is going to become fully reduced, yes.
So when you're doing this, it's not like it's not a series. It's not two parallel series.
It's not two parallel series. Yeah, it's series. Yeah, and I don't know how long it takes for the second electron to start on its way. Probably as soon as this guy loses an electron, I assume it could probably accept the second one. All right. So the point is that each of these iron sulfur has to act twice. The other thing is that this shows why it's important to have things like flavins and coenzyme Q that can accept 1 or 2 electrons, because you have other things like iron sulfur clusters that can only accept 1. So you need sort of intermediaries in that sense. The last point is that this second proton, to make the fully reduced coenzyme Q, also comes from the matrix side of the membrane. So that's what's shown on this figure. There's the 2 protons that end up in the coenzyme Q, the reduced coenzyme Q, and they are shown. The active site here is situated so that protons can enter from the matrix side. So that pretty much shows everything that happens. And again, we'll come back to these 4 protons on Wednesday. All right, so we finally, by this sequence of reactions, we've made reduced coenzyme Q. Again, it diffuses out of the active site, and it has to diffuse till it finds a complex 3. So complex 3 is sitting in the membrane, and this is the membrane. So here's the complex 3. And so the reduced coenzyme Q diffuses into an active site. And this reaction is actually complicated, and sometimes I've gone through it. I've decided I'm not going to go through the details because of interest of time. But we're just going to give the overall reaction. So the overall reaction involves cytochrome C, which is oxidized, has to diffuse to complex 3, where it can accept 1 electron, and then diffuse away. All right, so it becomes reduced, so it diffuses away, carrying an electron with it. This has happened twice, because coenzyme Q has 2 electrons. Again, it's good that coenzyme Q can give 1 electron to the first cytochrome C, and then give the second one to the second cytochrome C. If you read in the book, the mechanism is actually more complicated than what I just said. But let's leave it at that. All right, so that's where the electrons go. Both electrons end up being given to cytochrome C. What about the protons? This is the matrix side. Cytochrome C is on the other side. Where do the protons go? The protons go to the other side of the membrane. Right? So those were protons that complex 1 took them from the matrix side, but now complex 3 releases them to the other side. So that's proton pumping. That's a very simple way to get protons from one side to the other. Right now, so what's the overall reaction? You can write it like this. 1 reduced coenzyme Q plus 2 oxidized cytochrome Cs to make an oxidized coenzyme Q plus 2 cytochrome Cs that are reduced. All right, but now it's where it gets tricky is to account for the protons. All right, so here we're talking. So there, this is the overall reaction. The one. So what I just said is 1 reduced coenzyme Q plus 2 cytochrome Cs. In the course of this, 2 more protons are picked up from the matrix. And those 2 additional protons are released on the other side of the membrane. So you've got these 2 protons plus these 2. That's 4. And so the net result is that 4 protons end up on the P side of the membrane. And the reason it's 4 and not 2 is this complexity that I mentioned. So the 2 electrons go from the coenzyme Q to the 2 cytochrome Cs, 1 electron at a time. You oxidize only 1 coenzyme Q, but you move 4 protons and not 2. The precise mechanism is something that's known as the Q cycle, which is discussed in the book. I'm not going to go into it, but it was a mechanism that was proposed to account for this fact. It seems like it should be only 2 protons, but in fact it's 4. And so if you look at the book, you get a sense of how it works. Basically, the bottom line is that this is the net reaction, written up here a little more clearly. That's the net reaction, but there are actually multiple steps that enable more protons. Right, so this is complex 3. The function of complex 3 is to oxidize coenzyme Q. No matter where it came from, complex 3 will reoxidize it. And the protons always get released on the P side of the membrane. So again, this is a way to pump protons across the membrane. All right, so that's complex 3. Complex 4 I was going to say even less about, so I'm going to squeeze it in. It's a really important. It's important in the sense that it's where oxygen actually gets used. But the chemistry of it is complicated.
What would you think? I think someone just tried to
So I'm just going to show the overall reaction of complex 4. So complex 4 is going to take the electrons that's shown in this slide. It's going to take the electrons from cytochrome C and give them to oxygen. So the reduced cytochrome C has 1 electron. Let's look at the stoichiometry for 1 molecule of O2 or 1 mole of O2. All right, so the product of this reaction has to be water. Right, so they're showing us half a mole, but let's do this 1 mole. So from a mole of oxygen, we're going to get 2 moles of water. That reaction requires 4 electrons. So you actually need 4 reduced cytochrome Cs to reduce 1 molecule of oxygen. So that's going to produce 4 molecules of oxidized cytochrome C in the end. And so we also need 4 protons. So those protons are here, and they are coming from the matrix, and the water is released in the matrix. So that's the overall chemistry of the reaction. And again, as shown on the slide, 4 protons, well, no, not shown, they show 2. But for each molecule of oxygen, 4 protons end up getting pumped. Again, the pumping mechanism here is more like complex 1 that we haven't gone over. Right? And I'm not going to go through this one, it's supposed to be able to do complex 1. So this again is the overall process. If you want to do it from the standpoint of 1 NADH, which has 2 electrons, that's enough for yeah, that's enough for 2 protons to come. So that's enough for half a mole of oxygen to make 1 mole of water, and 2 protons are pumped. So that's the stoichiometry. This figure is showing for 1 mole of NADH everything that happens. Right? So you get 2 protons pumped per mole of NADH. So note that it's 10 protons pumped for 1 mole of NADH. So we'll come back to that. That's all I have to say about complex 4.